Hello and welcome to another lesson about formal language theory. In the last lesson we talked a little bit about how automata work, and we built a sort of vaguely specified deterministic finite automaton. In this video we're going to start talking a little more formally about how we describe an automaton, and specifically we're going to talk about deterministic automata. So this is a more formal version of a deterministic finite automaton than we had in the previous video, in that we've actually labeled everything in the sort of more formalistic way of how we do this. So what does this mean? This has our thick circle, which means it's our start state. So when we get fed a string like A, B, B, for example, you go in here, you land here, we can process an A, we're still in the same state, we process a B, we get here, B, and B, we're back to here. Since we're in a final state, which we can recognize because it's got two circles, that means that the string that we've processed is part of our language. This is the same automaton that is discussed, this is the example that's discussed in your book if you want to read what the book says about this automaton. But this is a more formal version of how we would draw that out. But now let's do a definition of exactly all the stuff that we need to know in order to build a system like this. So a deterministic finite state automaton, so you can either call it a finite automaton or you can call it a finite state automaton. What this means is that you have a finite number of states, right? So a finite number of circles that you would be able to draw, at least in theory, how many states you're going to go into, right? That's all that the finite means. Which we also call it a deterministic finite automaton, a DFA more commonly. So we'll see that'll be how it's written most of the time from here on out, just because this is a whole big mouthful. But one of these automata is actually just a quintuple of 5 things: a set K, a set sigma, a state Q0, a set F, and a relation, whatever this Greek letter is, I'm forgetting off the top of my head, but that Greek letter is the relation. So what K is a finite set of states. So K is basically just going to list off how many circles we have and what we've named them, and we name these with symbols, right? So in this case, the finite set of states for this particular automaton, the finite set of states is a set containing Q0 and Q1, since that's what we've named our different states in this case, Q0 and Q1. So that's what K is. And then we have the set sigma, which is a finite alphabet, and because it's an alphabet, that's going to be a set. And this contains all the symbols that we can have in our strings. So the symbols that we can have in our strings that are acceptable according to this automaton are A or B. These are the two different symbols we can use, so that's what our set sigma is going to be, B or A. Just listing them in backwards order just for fun. What Q0 is any state that is a member of K, right? You have to choose one of these and only one, and that one state will be your start state. So for us, we've just named it Q0, right? But we could just as easily have named it, F or, Bluebird or whatever. We wanted to name that state, we could name it that, right? But the name that we've assigned to this start state in this particular automaton is Q0. And then we have F, which is a set of states that are final or accept states. So in this case, we only have one final state, but we could create another automaton that would maybe have 2 accept states, right? So you can have any number of accept states that you want, right? Final states. In this case, we recognize that this is our final state. It's got 2 circles around it, so this is our final state. But even though we only have one final state, we still have to have it be a set. So a set containing only one final state is what F is, right? Is a set containing the final state, the except states. And this is the confusing one. A function from K cross sigma to K. So what the heck does that mean? So remember that when we do a set cross any other set, essentially what we're doing, if we have a set A and a set B, and set A contains X, Y, and set B contains AB, for example, essentially what you're doing is you're creating all the possible pairings where the arrows go in this direction, right? So you're creating all the possible ordered pairs with A as the domain and B as the range. So what would K cross sigma be in this case? K cross sigma would be a set containing ordered pairs where the left side is in K, so is one of our states, and the right side is one of our alphabet members. So we would have Q0, comma B. We would have Q0, comma A. We would have Q1, comma A, and Q1, comma B in a set, right? So this is K cross sigma, right? So that is the first thing that we're building is this set. Now, what does the second half of this statement mean? The rest of the statement says that you're taking a function from K cross sigma, which is the set we've just built, to K. So you're essentially taking this as your domain, and this is your range. Your range is going to be K, so Q0 or Q1. And you're going to build a relation so that this is on the left side and this is on the right side. But because we specified that it's a function, each of these can only be paired with one member of this, right? So let's do this over here. So this is going to be our sigma in this case is. We have an ordered pair in here. We're going to take this ordered pair, Q0, comma B, which we've just taken from there, Q0, comma B, and we're going to pair this up with Q1 in its own ordered pair, right? So this is just another ordered pair where the left side happens to be an ordered pair and the right side is just a state. So what does that mean? It means that when we're sitting here in state 0 and we want to add a B, we know that we want to add a B, what are we going to do? It'll take us to this state, right? If we're sitting here in Q0 and we want to add a B, it'll take us to this Q1 state. So let's do that for our other states. If we're sitting here in Q0 and we want to add an A, that'll take us to Q0, right? If we're sitting in Q0, if we're sitting in Q0 and we want to add an A, it'll take us to Q0, right? Now imagine that we're sitting in Q1 and we want to add a B. That'll take us to Q0. So we're sitting in Q1 and we want to add a B. That'll take us to Q0. And finally, if we're sitting in Q1 and we want to add an A, that will take us to Q1. And then that is our function. So how do we determine that this is a function? We have to check that for each of these pairs, it's only going to take you to one place. So what does that mean? That means that we can't have something like this, right? In this case, you have two options. For once you're in here, if you feed it a B, You could either loop there or you could loop there, and that is not allowed. So that's what the fact that it is a function says, is that you can't have more than one direction that you leave. If you're sitting in Q1 and you want to add a B, you have to go to only one place. You can't go to more than one place. You could be sitting in Q1 and you want to add a C and you don't have anywhere to go. That's fine. But you can only go at most to one other state if you want to add a new symbol. So this is the formal definition of a deterministic finite automaton. In the next video, we'll talk about how we can use this to navigate through an automaton in a more mathy looking way.